Hi, welcome back to this series of video lectures on kinematics of mechanisms, part A. So this is video number 2. In the previous video, we looked into what is degree of freedom of a point in 2D and 3D, and then we also looked into what is degree of freedom of a rigid body in 2D and 3D space. In this particular video, we'll be looking at GeoGebra. It's an open source and free software, very effective to learn any form of programming, and we'll also see how to write simple programs in GeoGebra to understand degree of freedom of a point in 2D as well as degree of freedom of a rigid body in 2D. In between we'll also do some formulation and we'll go back to the mathematics. Okay, let me open up internet browser. So the website that we are going to do is geogebra.org/geometry. Okay, so when you open it, you get some similar interface, and typically the good setting is we should know where the axis system is, and also we can look at the grid lines, so it looks more like a graph sheet which we are all familiar with. So the software is very good if at all you want to learn to draw some simple shapes. So for example, I can just create two lines and maybe create a segment between those two lines. Okay, so the coordinates of these points can be changed depending on your requirement. Similarly, there are a lot of other features in this particular software, like how to draw perpendicular line, parallel line, which we'll be using when we go to other form of analysis of mechanisms. And we can also look at this circle center radius. See, let's say I want a circle of radius 5 somewhere. Now I can move this circle around, and if at all I want to find the intersection between the line and the circle, so I can select a point and try to find out. You can see that I'm able to find the intersection between line and a circle. Now if I hit escape, so basically it becomes move. I can drag any particular shape and I can move around. Now what you observe is the letters point D and E are changing. Okay, similarly if I move this point, you can also see that the points D and E are changing. So A and B points initially we are defined, so they are independent. D and E are dependent on A, B, C as well as the radius. So this is a good way of understanding degrees of freedom as well. Okay, now why am I explaining all this is because we'll be using this information in the coming videos of how to find intersection between line and circle, or maybe circle and circle. If I have one more circle, very quickly, let's say I have a circle like this. So if I move this circle, sorry, yeah, I can move this point in this manner. Now I can also find out the intersection between two circles as mentioned here. Sorry, I should drop it correctly, so I should go near the intersection point. Yeah, that is how it is. Now if you observe carefully, if I move this circle, the intersection point is also changing. So that is what we want in our course as well. Okay, now the fun part of this mechanism is the user interface is also there, and the equivalent code will be seen when you click on this algebra calculator kind of symbol. If you observe, this is nothing but code that has been generated automatically. Okay, so a good way to learn programming if you're not so good in programming is to use GeoGebra to get confidence, and later on you can move on to any other programming language. Now whatever we have done, let us also try to see if we can use this programming interface in the coming few classes. So first and foremost, let me just clear all whatever I have drawn. I don't have to save it, so I'll just discard, and we start fresh. So I'll click on show axis and major and minor grid lines. Okay, now right now if you go back to the previous video, we had looked at how do we represent degree of freedom of a point. That means if I give you the value of px and py, you should be able to draw a point. Okay, let's do that. in the code I'll start typing p capital X is equal to, let's say, 2, p small y is equal to, let's say, 3. Okay, so I have defined two parameters. Now I can define a point as capital P is equal to px comma py. So this is a syntax to create a point in GeoGebra. So the capital letters represent points, the small letters variable beginning with small letter can represent a vector, scalar, like that. Okay, so please be careful whenever you have a point, use a capital letter. Okay, now px and py, you observe that it is gray. That means I can't possibly, okay, I can still move it because it is not constrained by anyone. So okay, something happened here. Okay, now px, if I change the value here, you see that the point got changed. Similarly py. Now initially we had seen that degree of freedom of this system is 2, so that means I can create a slider for this. So if you see this, I'm able to translate along x-axis. Similarly, I can create a slider for y. I can translate along y-axis, and I can also do both. Okay, so we have understood that two independent parameters are there to move a point, or two independent parameters are required to represent a point. Both the definitions of degree of freedom we have understood now. Okay, so this is if you directly know the coordinates. Now if someone asks you what are the values of r and theta, so you can always use a programming. So I used r is equal to sqrt open bracket, then px into px, into is given by star, plus py star py. So that is the value of r. Maybe it is rounded off, that is why it is coming in that manner. Now theta is equal to, you remember that we had used a tan 2. So a tan 2 will, if you observe here, it takes y component and x component. So a tan 2 py comma px. So it is given in degrees, but typically in MATLAB, okay, a tan 2d I have used. If you use a tan 2, you will get it in radians, but sometimes it is shown in degrees. Okay, now what we have to do is, let's say we clear. Okay, there are a few kids playing out, please don't mind. Discard. When I discard, we have show axis, then we have major and minor axis. Now let's look at the other way of doing it. If I give you the value of r is equal to 4 and theta is equal to, let's say, pi by 6. Okay, I want to give it in radians. Now px is equal to, we have seen here in the formulation, if r and theta are given, px and py are determined using r cos theta, r sin theta. This is a very common set of equations we find in mechanisms as well as in robotics. So if you don't know this, then obviously you will not be able to succeed well in both the fields. Okay, so let me say r cos of theta. Now please remember, in software languages, cos and sine, we always should enter radians angle. Px py is equal to r sine of theta. Okay, now where is the point? Point is not there yet, so I'll have to do px comma py. So that is the point P. Now let's say I create a slider. Now you can see that I'm able to move by the radius, radially inward and outward. Similarly, I can also, okay, settings, I can go slider, minimum, let's say 0, maximum 2 into pi. Okay, instead of oscillating, I'll say increasing. Right, Now with that, why am I not able to see slider? One second. Show object, slider. So usually it is seen. Show slider. Okay, show slider. I hope it will come. Okay, let me try it 0. Maybe it will come then. Okay, sorry. So maybe that pi, sometimes this behaves in that manner. Now if you observe, let me increase R substantially. From theta equal to 0, if I move, the point is moving on a circle. Okay, so that is what is a parametric equation of a circle as well, r cos theta and r sin theta. If I use this play button, you can see that the point is actually, the theta value is changing, accordingly px py values are changing, and accordingly the point is moving on a circle. Okay, now if at all you want to trace it, you can also use the trace command. Right click and show trace. Now as the point moves, you will be also able to look at the trace. Okay, so what we have covered so far, we looked at if Cartesian coordinates are required, how do you find polar coordinates? If polar coordinates are given, how do you find Cartesian coordinates, and also animate? So this is part of degree of freedom of a point. Now let's go back to the digitizer. So let me try to explain what is degree of freedom of a rigid body and how do we show that in GeoGebra. Okay, if I have a 2D system, let's start with the 2D system. If there are a rigid body, so we have understood that there are 3 degrees of freedom, 2 translation and 1 rotation. Okay, now we can also assume that there is a coordinate system that we have put attached on this rigid body. Okay, so this is on the body. So if I move the body, so the coordinate system attached will also move along with it. Okay, so there are 2 ways of looking at it. One, I move the body, coordinate system moves with it. Second is I move the coordinate system, and once I move it, I draw the rigid body. Okay, so what we also can do is we only consider, let's say there is a coordinate system xy and there is another coordinate system, let's say uv. Okay, now how does this, now what is the degree of freedom of this system? Again, I can move this along x-axis, I can move axis along z-axis, rotation is also possible. So degree of freedom of this system is now 3. Now mathematically, if I want you to represent the same, I can't just say that okay, move it along x, move it along y, and that, right? So it's better we represent in a different manner. So let's see, I have sorry, that is not required, sorry for that. Okay, what I'll do is I'll basically draw a parallel line to x-axis. Now what are the if I call this as O and this as, let's say, D, so there's a vector here. This OD vector will have coordinates dx, dy. Okay, and if I want to represent the orientation, I can represent using this inclination of u axis with respect to the horizontal. So obviously when I mean that, this angle also will be theta. Okay, so what we end up is we need 3 degrees of freedom. So that means I can give you the value of dx, dy, and let's say theta. If I give you this much information, you will also be able to draw that coordinate system. Now there is something known as HTM. Again, this comes in robotics, but I just want to very briefly explain here because we are going to deal with some animations in the mechanisms. So it's good that we know that part. Okay, so HTM means it has information about the orientation of that U frame, and it also has the position information dx dy, and let's say the third row is of this form 0 0 and 1. Okay, now dx dy is already known to you. Now what is this q matrix? Q matrix is known as direction cosine matrix or rotation matrix. So it basically has components of ux, uy, vx, vy. Now what are ux, uy? So this u vector is considered as unit vector. Okay, similarly v vector is also a unit vector. Now what is ux? If you remember, if this length is 1 and the component of that vector will be the projection along this line. Okay, so 1 cos theta, r cos theta, r sin theta, if you remember, right? So this is going to be cos theta, 1 into cos theta. Similarly, the vertical length will be 1 into sin theta. The v component means this vertical height will be sin theta. Okay, now vx means what is this projection, this guy. Now if you remember, we had come up with a convention that the angle should always be measured with respect to the positive x-axis till that vector. So this angle is 90 plus theta, because this is 90, there's already a theta, so I'll write cos of 90 plus theta. Okay, similarly the sine term will come here, sine of 90 plus theta. So let me complete the HTM because we'll be using this HTM soon. So HTM will now have cos theta sine theta, cos theta sine theta, and let's say this cos of 90 plus theta is minus sine theta, and sine of 90 plus theta is cos theta. Okay, and finally we already have dx and dy, dx dy, and the last row will be what below the position will always be 1 and left side of that will be zeros. Again, this is a standard terminology used in robotics, but I just want to introduce it here because in few mechanisms we'll be using this HTM matrix as well. So this is 3 cross 3 for a 2D system. Okay, now what we are going to do is we'll try to replicate this in GeoGebra. Okay, so please follow through. I'll clear all, discard. I'll go to axis, show grid, major minor axis. Okay, so I want xy direction is already given, so we need a point D and an angle theta, right? So those are the three independent parameters. Let's write that. So d capital X is equal to, let's say I'll put zeros for now, d capital Y is equal to 0, capital D is equal to dx comma dy. So that is capital D point. Now I also require theta variable, I'll put it as 0. So basically you have dx, dy and theta, three parameters, independent parameters, because degree of freedom of that UV frame or coordinate system was 3. Okay, now how do I get the u and v vector drawn? Okay, so let me go back to the GeoGebra now, sorry, the digitizer. If I have D here, and if I want to get this point, let's say U, okay, let me try to take a different angle so that it doesn't cause any confusion. Okay, let me say point U is here. Okay, now dx dy, if you are given, dx and dy will give you this vector. So this is value of dx, value of dy. If I want to find the point U, right, let me put this as capital U, sorry, yeah. If I want to find the value of U, what I should do is, this will be dx, this will be 1 cos theta, because this is 1 and this is theta, so dx plus 1 cos theta. Okay, so ux is going to be dx plus 1 cos theta. Similarly, uy will be dy plus 1 sine theta. This part, this is 1 sine theta. Okay, so we have got this. Now what else do we need? Let's say I want to find value of cap point V, the tip of this. If you observe, this guy will be 90 plus theta, so dx plus 1 into cos of 90 plus theta, so I'll write it directly. Vx will become dx plus cos of 90 plus theta is minus sine theta, minus 1 sine theta. Similarly, Vy is equal to dy plus r sine 90 plus theta is cos theta, 1 cos theta. Okay, so this value is what we'll be using in the GeoGebra now. So I need to find the point U. Ux is equal to dx plus cos of theta. 1 cos theta is cos of theta. Sorry, yeah. Similarly, uy is equal to dy plus sine of theta. So I'll write capital U is equal to ux comma uy. So this requires some practice. I think whoever is watching this should also try to pause the video, do it, just don't watch it. Vx we have found out as dx minus sine of theta. It was just derived a while ago in the digitizer. Vy is equal to dy plus, sorry, plus cos of theta. Okay, obviously V is equal to, capital V is Vx comma Vy. So both the points have come. Now let's draw vectors so that it becomes easier. Vec du or vec u, vector. Please note small letter V I have started because the variable should start with a small letter for a vector. I'll create as vector. Now vector function will require, there are two ways of doing. One is position vector, you just give some point, it will go there. or you define what is the start point and what is the end point. So in our case we know the start point and end point, so I'll say start point is D, end point is capital U. Similarly, vector V is equal to vector between D and capital V. Okay, now just to play around, I'll make this color red, because usually in CAD software and other places we have color. X-axis is red, green for y-axis. Okay, I think we are almost coming to the end of this video. So if you remember, we had 3 degrees of freedom. So let me create sliders for dx, dy and theta. Okay, now if I just move dx, you can see that the coordinate system is also moving. That means I can assume that there is a rigid body that is moving. Similarly, when I do this, I can see that this guy is also moving. And then finally, when I do theta, what you see, it will rotate like this, right? So once you know the details of dx, dy and theta, you know where the coordinate frame has reached. So in the coming videos, we'll be using this information for, let's say, drawing a slider in a slider crank mechanism that is on an inclined plane. So that is why this derivation was important. So please stay tuned for the remaining tutorials. Thank you.